This is the screencast for section 10.3, example 8. Now we're going to find the area between two polar curves. So first of all, the area between two polar curves is this, what potentially looks very messy. Basically, we're taking the area of the outer curve and subtracting the area within the inside curve. And then we get this shorter version. So we have the sum of the outside sectors minus the sum of the inside sectors. In other words, if I have this sector that stretches all the way to the outside curve, I'm going to then subtract out the sector from to the inside curve, leaving me with what is between the two curves. So let's look at example 8 here. Find the area of the region that lies inside the circle r equals 1 and outside the cardioid r equals 1 minus cosine of theta. Alright, so if we have, there's a picture over here. Here's a circle of radius 1 inside that circle, but outside this cardioid. Well, I first need to find out what rotation I'm dealing with. Where do they intersect down here? Where's the lower limit and the upper limit? And I know it says negative pi over 2 and pi over 2, but I want to set those two curves equal to each other. So I have r equals 1 and I have r equals 1 minus cosine theta. So wherever those two r's are equal to each other, that's their intersections. So I'm going to solve, and I get negative pi over 2 and pi over 2, which does seem appropriate. Negative pi over 2 and pi over 2. So that means I'm going to take the area from negative pi over 2 to pi over 2 of 1/2 times the outside radius. So the outside radius here is just going to be 1. That's the circle. And I'm going to subtract the inside radius, this little piece of the cardioid, which would be 1 minus cosine theta. Again, only going from negative pi over 2 to pi over 2. I don't need to worry about what's going on over here. And then d theta. Simplify a little bit, and I get, after I take the integral and evaluate, I'll get 2 minus pi over 4, which is 1.215 square units. Then out try problem number 53, says find the area of the region described, and that's going to be the area shared by the circle r equals 2, so with radius 2, and the cardioid r equals 2, 1 minus cosine theta. So I've graphed that here, and I'm trying to think of a strategy. I'm trying to find this area inside. Now, it does seem like, you know, we're in this part about outside minus inside, but this is all on the inside. This whole area is on the inside. So I'm actually going to split this inside area into two pieces. I'm going to say that inside area is this right piece only determined by the cardioid, and then plus the left piece only determined by the circle. Makes my life a lot easier. Now I just need to find out what thetas I need to use. So I'm going to set the circle equal to the cardioid, find out where theta will have the intersection. So that's negative pi over 2, 3 pi over 2, some sort of pattern like that. Which means now I could take the right piece and add it to the left piece. Now that right piece, right here, is only determined again by the cardioid. That cardioid looks like it's going to rotate from negative pi over 2 to pi over 2. And then its radius will be squared, of course, d theta. Now the left piece is this circle. So its radius, it rotates from pi over 2 all the way down to 3 pi over 2. I wouldn't say negative pi over 2 to pi over 2. I guess you could do negative 3 pi over 2 to negative pi over 2, but may as well just do pi over 2 to 3 pi over 2. And then its radius is 2, and then of course squared. I evaluate that and I get 5 pi minus 8 units squared. So we are not always doing something complicated. A lot of times you'll have to graph and come up with a good strategy to find the area that's being asked of you.